In 1995, the Kobe earthquake hit Japan. Buildings collapsed, highways snapped, and over 6,000 lives were lost. Yet one structure, a 10-story office building, stood almost untouched while everything around it crumbled. Why? Not luck. Structural dynamics plus earthquake engineering. That building survived because engineers had designed it for the one force you never see coming: seismic motion. Structural dynamics and earthquake engineering deal with how structures behave when the ground starts moving. Unlike static loads, earthquakes strike suddenly, change direction rapidly, and release massive energy in seconds. Understanding that behavior is the only way to prevent catastrophic failure. 1. What makes earthquake loads different? Earthquakes don't apply force, they shake the ground beneath a structure. A building's base moves. Its mass resists. This creates inertia forces, which behave like internal whiplash inside the structure. These are called seismic loads and depend on ground acceleration, mass of the structure, stiffness, natural frequency, damping. If a building's natural frequency matches the earthquake frequency, resonance collapse risk skyrockets. 2. Fundamental concepts. A. Natural frequency. Every structure has a frequency at which it naturally wants to vibrate. Tall buildings, low frequency. Short, stiff buildings, high frequency. B. Damping energy dissipation. The more damping, the less violent the vibrations. C. Mode shapes. The different ways a structure can deform during vibration. D. Response spectrum. A curve engineers use to estimate maximum expected seismic forces. These are the backbone of seismic design. How engineers make buildings earthquake resistant. Earthquake engineering uses two main strategies. 1. Increased strength and ductility. Reinforced concrete detailing, shear walls, cross-bracing, moment-resisting frames, strong column, weak beam philosophy. Energy dissipating devices. The goal, a structure that bends but does not break. 2. Reduce earthquake forces. Reaching the building. This is where modern engineering shines. Base isolation. Rubber bearings, lead cores, and sliding bearings are placed under the building. They allow the ground to move while the building stays relatively stable. This reduces seismic forces by 50 to 70%. Energy dissipators. Devices that absorb vibration energy the way shock absorbers work in cars. 4. Real-world example. Japan's Sendai Mediathek survived the 2011 Tohoku earthquake, one of the strongest ever recorded. Why? It used flexible structural tubes designed to deform safely and absorb energy. The lesson: earthquake-resistant design isn't about making a building unbreakable. It's about making it smart enough to survive. Structural dynamics and earthquake engineering turn unpredictable ground motion into predictable engineering behavior. If the calculations are right, the detailing is correct, and the system is well designed, a building can take the hit and still stand. Want the next topic in the same crisp, story-driven format?